Capacitor is a device that stores electrical energy. It is mainly used in filtering and timer circuits. In this video, I will mainly focus on the workings of a capacitor. Let's get started. This is a capacitor. Inside this, you will find two metal plates and a dielectric. The two metal plates are separated by the dielectric material. It is basically an insulator, so current cannot flow through a dielectric material. I will talk about this later, but now let's focus on the plates. The atoms present in each plate is initially neutral, which means that every atom has equal number of positive and negative charges. Positive charges are protons, negative charges are electrons. Only electron moves in an atom. So each plate has neutral atoms initially, and because it is neutral, there is no voltage across the capacitor. However, if you connect an external power source across the capacitor, such as a cell, the positive terminal of the cell will pull the negative charges from atoms of the plate, and the plate connected with the negative terminal of the cell is filled with negative charges. The result is a net negative charge on one plate and a net positive charge on the other plate. We know that opposite charges attract each other. So in the capacitor, the charges in each plate attracts each other. But because of the dielectric, electrons from one plate cannot go to the other plate. Now, even if the power source is removed, the charges will still be in the plates because of the positive-negative attraction, and there will be a voltage across the capacitor which can be observed using a voltmeter. This process of transferring electrons from one plate to the other using an external power source is called charging a capacitor. The charges stored in a capacitor equals the charge that has transferred from one plate of a capacitor to the other. Also, just like using a phone after charging it, a capacitor can also be used after charging. For example, if I connect a bulb at the terminals of a charged capacitor, the voltage of the capacitor will be enough to light up the bulb for a little time. This process is called discharging a capacitor. This is what happens when a capacitor discharges. The electrons from the negatively charged plate really wants to go to the positively charged plate. Electrons would go to the other plate directly, but the dielectric material prevents this. Now, when a load such as a bulb is connected across the capacitor terminals, the electrons finds an easy path to flow to the other plate. The electrons flows through the bulb and it lights up. Finally, all the transferred negative charges come to the positive plate of the capacitor, and again the number of positive charge in each plate equals the number of negative charge, which means that the plates are neutral again. So the bulb stops glowing and we can say that the capacitor has completely discharged. Capacitance is the measure of how much charge a capacitor can store in a voltage. Let's take an example. Consider this small bucket. How can we measure how much water this bucket can store at a certain water level? Well, we can do simple math like this. Capacity of the bucket to store water equals to water stored on the bucket in liters divided by water level in meters. For example, say this bucket can store 5 liters of water at a water level of 1 meter. So, using the capacity equation, we can say that the capacity of this bucket is 5 liters divided by 1 meter, which equals 5 liters per meter. If another bucket can store 10 liters of water at the same water level, the capacity of the second bucket is therefore 10 liters per meter. We can say that the second bucket has more capacity than the first one. Similar to the bucket, a capacitor has a capacity for storing, but not water, it is charge. The water level of the bucket can be thought of as the voltage across a charged capacitor. Also, water on the bucket can be thought of as the charge the capacitor has stored, which we already discussed. The simple math that we did to find capacity of a bucket can also be used to find capacity or capacitance of a capacitor. Capacitance equals to charge stored in a capacitor divided by voltage across the capacitor, or in short form, C equals to Q divided by V. The unit of charge is coulomb. 1 coulomb equals to 6.25 times 10 to the 18 electrons. It's a huge number of electrons. And the unit of voltage is volt. Let's take an example. 2 capacitors are charged to 1 volt. Charge stored in the first capacitor is 1 coulomb. So using the formula capacitance equal to charge divided by voltage and putting the values, we get capacitance of 1 coulomb per volt. This C by V unit is a farad named after Michael Faraday. So capacitance of the capacitor is 1 farad. In the second capacitor, at 1 volt, the capacitor can store 2 coulomb of charge. So capacitance of this capacitor equals 2 coulomb divided by 1 volt, which equals 2 farad. So we can say that the second capacitor has more capacitance than that of the first one. To understand the difference, let's take the previous bucket example. We have 2 buckets of which one can store 5 liters of water in 1 meter water level, and the second bucket can store 10 liters of water in 1 meter water level. Now, if we drain the water from each bucket using same thickness pipe, it is obvious that the large capacity bucket will be able to supply water longer than that of the small one. Similarly, if you take 2 charged capacitors, each of capacitance 1 farad and 2 farad, and connect same load in each capacitor, the high capacitance capacitor will be able to supply current longer than that of the low capacitance capacitor. When a capacitor is charged up using a power source such as a cell, it charges the capacitor until voltage of the power source equals voltage across the capacitor. You can think like this: the voltage of the power source pulls electron from a plate of the capacitor. But as the capacitor builds up positive and negative charge, the voltage of the capacitor starts increasing, and at some point, pull of the power source in the electron equals pull of the capacitor in the electron. In other words, V of the capacitor equals V of the power source. As an example, if you charge a capacitor of 1 farad using a cell of 1.5 volts, the capacitor will charge until voltage across it becomes 1.5 volts. To find this, you need to use the capacitance equation. Capacitance equals charge divided by voltage. Put the values of capacitance and voltage and solve for charge. We get charge equals to 1.5 coulomb. A capacitor having capacitance of 1 farad is usually a very large value. Typical capacitors have capacities in picofarads, nanofarads, and microfarads. Let's discuss an application of capacitor, DC ripple filtering. Consider a cell of 1.5 volts. The voltage waveform at the positive terminal with respect to ground will look like this. It is a constant 1.5 volt. But now consider this power source. The output voltage waveform look like this. It is still direct current because it is above zero of the voltage axis. But to make it a continuous DC, we need to use a capacitor at the output like this. What capacitor will do is charge at the peak voltages and discharge at the gaps. The result is a constant DC voltage. This is called filtering. However, a load may make the voltage discontinuous, but it is negligible compared to the capacitor-less voltage output.